In this video, we will learn how to solve the problem of transient species diffusion in a 2D saturated porous media. In this problem, we consider a rectangular domain where the concentration of a species is initially 0 everywhere. At time equals 0, the boundary at the right boundary, the concentration is changed to 1. The bottom, the top, and the left boundaries are all said to be zero flux boundaries for the species. So the boundary condition at the right boundary is species concentration equals 1, and at the bottom, top, and the left boundaries, the flux of the species is 0. For ease of comparison with the analytical solution, all the solid and the fluid properties are set to 1. That is, the fluid density is set to 1, as is the rock density, and the molecular diffusivity of the species in this medium. The soil porosity is also said to be 1. The distribution coefficient and the longitudinal and transverse dispersivities are said to be 0. We will solve this problem in the transient mode for 1 unit of time. Initially, there is rapid change in the concentration near the right boundary. As time increases, this rate of change decreases. So, as we solve the problem, we can afford to reduce it or increase the time step. With an initial time step of 5 into 10 power minus 5, and time step is increased by a factor of 1.05 after every time step. The maximum time step is limited to 5 times 10 to the minus 3. We can compare temperature versus x at different times and plot it against the analytical solution. The analytical solution can be found in the book Karslaw and Nager, and this plot shows a comparison between the PORFLOW simulation and the analytical solution. The plot is x versus concentration at different time instants. Next, we will see how to solve this problem using PORFLOW. The CFDStudio GUI will be used to set up the problem and visualize it. From the desktop, double click on the PORFLOW icon to start PORFLOW. Now click on the new project option to set up a new project using CFDStudio PORFLOW and click on go. Now the problem we are solving here is species diffusion in a 2D porous medium with zero flux boundaries in one direction. So the diffusion happens only along one direction. Even though the problem domain is 2D, due to the boundary conditions, the species transport happens only in one direction. Now the first step in creating a project using CFDStudio is to give a title for the project in this box. The user should only use alphabets, numbers, and the underscore button for the project title, and it is mandatory and extremely important not to use any space within the project title. So the space should be a continuous set of characters which are only alphabets, numbers, or underscore character. Let us give the title project 001. Now you can see a box for the directory in which the project contents will be stored, and the final folder has the same name as the project title we have given. Remember this location for the project folder. This is where all the files related to the project will be saved by CFDStudio. Now this project dimension is 2D, so leave this option of problem dimensionality at 2D, and the coordinate system is Cartesian. Now click on next. This problem is transport of species in a 2D box, a rectangular box. Now there is a very quick and easy way to create a mesh for such problem geometry in CFDStudio. Under the grid option, select the second option here of simple geometry. Now this will let you create quick grids for rectangles and squares in 2D and cubes, cuboids in 3D, and similarly circle in 2D and a sphere or cylinder in 3D. Now since this is a 2D problem and the geometry is a square, select the first option here, box orthogonal grid. You will see this dialog. Now you will see two requests for input here, the starting coordinates and the ending coordinates. For a box, the starting coordinates means the lower left. For example, if this is a rectangular box, this corner will be the lower left, and so the starting coordinates. This will be the upper right of the box and hence the ending coordinates. In our case, let us leave the starting coordinates at x equals 0, y equals 0, and the ending coordinates at 1 and 1. Now come to the number of nodes. We have seen in a previous video what the nodes, vertices and elements mean in the context of CFDStudio and PORFLOW. For a structured grid, when you say 12 nodes, that is equal to 11 vertices and 10 elements. So you have 10 distinct finite volumes in the x direction. Now change the j max in the this box to 3. So this means the maximum number of nodes in the j direction is 3, which means the number of vertices is 2 and the number of elements is 1. So the number of elements in the j direction is only 1. Now click on finish. So now we will see the PORFLOW problem setup wizard here. Before that, you can see the grid that we have created has been displayed here on the geometry panel. You can see that you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions in the x or the I direction and only one division or one cell in the j or y direction. Now this problem is species diffusion in a porous medium under saturated conditions. So leave the problem type to be saturated flow. The problem we are solving is unsteady, that is the solution changes with respect to time, and we want to see how the solution changes with respect to time. So click on transient problem and now choose the mass transfer option because this problem involves species transport, and leave this density specification option to be constant fluid density. We are not changing the density of the fluid as a function of time or space or any other variable. Click on apply. Now you will see the step-by-step PORFLOW problem setup wizard. The first step in a problem setup after the grid has been created is to create regions or subparts of the grid and give them names so that later we can set boundary conditions or sources or obtain specific output of variables at specific locations in the grid, or if you have multiple soil types, you can create different parts of the grid with different names and later apply different soil properties, transport properties, initial conditions, sources, and things like that. In this case, there are no sources and there is only one soil type, but we have different boundary conditions at each of the boundaries. So we will create names for different boundaries so that we can later apply boundary conditions for those boundaries. Now select this option of IJK window structured grid option and let us start creating the required regions. Now give the name left underscore boundary. So this will create a name for this boundary. Now set the lower left eye to 2 and 2 and upper right to 2 and 9. Now select the option convert to locate pair. In a previous video we saw what is the difference between a locate pair and a locate list. So locate pairs at the boundaries are used to set the boundary conditions. So now select the X minus option and click on create. Now let us see and click now close. Let us see the region that has been created. First, turn off this outline. You can see the axis and the outline has disappeared. Can be brought back by turning it on. Let us turn it off for now. Turn off the ruler, so the ruler and the markings have gone. Now double click on this button. Now you will see a window which says select region. Now go to the visibility option. So the region that we created, left boundary, is listed here, and under visibility it is checked on. You can see at the left boundary there is a blue line here which shows the left boundary. If you turn it off, you will see that it has disappeared. You can turn it on again. Go to selection and you will see the region now appear here again. Now you can change the color in which the boundary is displayed. So this is purely for display purpose only. So you can go and change the color to green. So it changes to green. And go and change it to red. So now it has become red. So this is purely for display purpose only. Click on close. Now click this option again. So we have some more regions to create. So click on the IJK structured grid option. Change the name to right boundary and change the lower left I to 999, the upper right I to 999, and from convert to locate pair, select the option X plus. Now click on create. So you can see the boundary here has been colored in light blue, and this boundary is called right boundary. Now let us create a region for the bottom boundary. Change the name to bottom underscore boundary. Now change the lower left I to 2. Leave the lower upper right I to 999. Leave this at 2 and change this to 2 and select Y minus. Click on create. Okay. The boundary has been displayed in black color, so you can't see it on top of the grid. We will, after creating the regions, we will see and confirm that the region has been created properly. Now once more, change the name here to top boundary. Change the J for the lower left to 999 and the upper right J to 999 and select the option Y plus and click on create. So now you can see that has been created. So close. Let us verify the regions have been created correctly. Double click on this, go to visibility. Now come back to selection. The top boundary is displayed in gray. Let us change the color to orange. You can see an orange line here. This is the top boundary. Go and select the bottom boundary. Change the color to yellow. So this is displayed in yellow. Now let us display all the regions together. Go to visibility, click all of them on. So the left boundary has been selected and it is displayed in red. The right boundary has been selected, it is displayed in blue. The bottom boundary is already displayed in yellow and the top boundary is displayed in orange. Now the user can change the color for any boundary to any color. So let us choose the left boundary and change it to yellow. So it's displayed in yellow. Go back to visibility. You can see both the left boundary and the bottom boundaries are displayed in yellow. It is purely for display purpose. This doesn't mean anything else. Okay, now close. Now let us go to the next step of the problem setup. Click on next here. There are no inlet outlets and so on in this problem. So click on next. By default, when a problem is solved in PORFLOW, the initial conditions for all variables is set to 0. So you do not have to explicitly set the initial condition for any variable to 0, but it is good practice to do that to make the input file clear. So click on initial conditions and select the dependent variable. Now so click on this arrow. Now you will see all the dependent variables in PORFLOW listed. Use the mouse button and scroll down and you will see a variable named C. C is the default transport variable name in PORFLOW. So click on this. Leave this option to replace previously specified. We will see what these other options mean in a different tutorial. Now this initial condition applies to the entire domain and we want to set the initial condition to be 0. It's not a functional form or a table, but it's a constant value of 0 which applies to the entire domain. So click on apply. Close. Now we have to set the boundary conditions for the problem. So click on this button to open the boundary conditions window. Now again go and select the dependent variable to be C. Now as we saw in the problem definition, C is set to 1 at the right boundary. It's the value of C. So the dependent variable is C. What we are setting at the boundary is the value, the Dirichlet boundary condition. Now come down and this is set for the right boundary. So click on this option called region and from this list you can click on this and you can select the right boundary, and the value we want to set for C at this right boundary can be set from the other conditions tab. So click on this and choose the constant option and say 1. Click on apply. Next we want to set the gradient of C at the left boundary to be equal to 0. So from this part of the window select the gradient option and we want to set the gradient at the left boundary. Now go to other conditions and the gradient at the left boundary for C is 0. So change this to 0 and click on apply. Now we want to set the flux of C at the bottom and top boundaries to 0. So C is only transported from the right to the left boundaries. Nothing comes in or goes out through the bottom boundary or the top boundary. So choose the flux option, and from select region choose bottom boundary. From the other condition, you can leave the value to be 0 and click on apply. Again, we have to set the top boundary also to be 0 flux. So come to select region and select the region top boundary, and from other conditions leave the value of the flux at the bottom top boundary to be 0 and click on apply. Now we have set all the boundary conditions, so click on close. Click next. We are not setting any properties for the fluid, viscosity or density. We will leave those at the default values. Click on next. Now we want to set the density for the solid matrix, which means the soil. So click on the material density option and select this option which says specify density, and we will set the density equal to 1. So leave this at 1, and this applies to the entire domain. Now if we had multiple soil layers, we can give different values of density for each region, and we can select a particular region and set the density for that region. But in this case we have only one soil layer, so leave it at entire domain and click on apply. Now we will set the porosity for this soil, so click on that and check this specify porosity option, and we will set the effective porosity for this soil to be 1. If required, we can specify total porosity and diffusional porosity. Please check the manual of PORFLOW to understand what effective, total and diffusional porosities mean. We can set different values for each of these. And since we have only one soil in this problem, this porosity value will apply to the entire domain. So click on apply. Now finally we want to set the transport properties for the species in this soil. So click on this button to open the options to specify the transport properties, and the transport properties are applied for the species C. We have a saturated flow, so there are no multiple phases, so don't choose anything here, and we are going to set constant values for these transport properties. We will choose the partition coefficient to be 0 and set the molecular diffusivity of the species C in the soil to be 1, and this applies to the entire domain. Click on apply. Now click next. If we have any sources or sinks in this problem, we can specify them here, but we do not have any sources or sinks, so click on next. When any problem is solved by PORFLOW, at the end of the problem the solution is written out to a file whose name is the project name, and the extension of the file is SAV. This is done by default, the user doesn't have to do anything, but let us go ahead and specify it, and we can change the file names if required and choose other options also, but for this problem we will leave those at the software defaults and click on apply. Now click on next. We will not specify any convergence criteria, we will leave them to be at the default settings, and we will not choose any matrix solvers also, we will leave that at the default values. Next, click on next. Finally we come to the specification of the time period for which the problem is to be solved. So click on this. So you have two options here called manual mode and automatic mode. For now, we will choose the manual mode. The period of solution, let us choose it as 0.02, and I'm not specifying any units for the time. As we have discussed in a different video, PORFLOW does not assume any system of units for any value specified, whether it is the coordinates, whether it's the initial or boundary conditions, whether it's the fluid properties or the solid properties like transport properties, hydraulic conductivity, thermal diffusivity, species diffusivity, or the time period, time step, gravity, acceleration due to gravity, specific heat, thermal conductivity, and so on. It's up to the user to give all the quantities in a consistent set of units. Now choose the time period for solution to be 0.02 units and change the time step at the start of the computation to be 0.00005, and we will examine the variable time stepping option here. So choose this, choose the geometric multiplier to be 1.05. What this means is the first time step will use a delta t of 0.00005 time units. For the next step, it will be 1.05 times this value, and the third step will be 1.05 into 1.05 into this. Now if you leave that, keep doing that, after some time the time step will become very large. So there is an option to give a maximum value for the time step. We will set it as 0.05. We will not change these other default values, and we will not select any variables. PORFLOW is intelligent to know which variables to solve. So click on apply. Now PORFLOW lets you give multiple solve commands in the same input file, and each one can have its own set of time step settings. So choose the solve option again. We've solved previously for 0.02. Let us now change it to 0.98. So totally we will solve the problem for one time unit. This time remove the variable time stepping option and choose the maximum time step to be equal to 0.05 and click on apply. So we have done with all the steps of the problem setup. Now click on finish. Now you will be asked whether you want to save the changes you have made to the project. Click on yes to save the problem setup. Before we do anything, now go to file. You will see an option here called view project files. You can see the location where we have stored the project files is given the same name as the project title. This is what we saw in the beginning, and these are the files in this folder. This project001.inp is where the commands that we set up are stored in a text file. So click on this and click open or view. Now you can see whatever is displayed in this command window is the same as what is in this input file. Click on close. Now scroll down here. Now you can see there are two solve commands. The first one solves for 0.02 seconds, second solves for an additional 0.98 seconds, totally 0.02 plus 0.98. So this solver will give the solution of this problem after a period of 1 second. Now to start solving the problem, go to this menu bar and you will see a button with a green triangle in it. If you take the mouse over it, you will see the caption run project. So click on this. Now you will see the during the runtime the convergence index and solution at a particular monitored location is displayed graphically here. After the solution is process is successful, you will see a window here which says view project files or start post processing or visualizing results, or you can do none of this and close this dialog. In this case, we will visualize the results for the problem we have just solved. So click on this option and now you can see the color contours here. So what is this being displayed here? First of all, go to this menu bar and you will see an option here. To take the mouse over it, it says toggle legend visibility. This will give the or display a legend for the colors here. So click on this. This is on and you will see the legend for the colors here. So the variable for which the solution is displayed is C, and the colors mean different values of the solution for C. Now click on this button or double click on this button. If you take the mouse over it, it says toggle contours visibility. So double click on this and you will see this option called contours, and you will see the solution is displayed for the scalar variable C. Now you can see some information about the solution. When it is the solution being displayed is at time equals 1.0, and this is step number 83, and you can see the minimum value of C in this domain is 0.875944 and the maximum value is 1. And you can see what is the contour type here: wireframe, fluid, isosurface, and so on. The default contour type is fluid. You change it to isosurface, you can see only lines being displayed. Now the colors, so let us change it back to flood. The user has an option of different types of coloring for the contours. You can change it to, by default the option is called rainbow, where the blue color is used for the lowest or minimum value, red is used for the maximum value, and green is for the middle, and there is a gradation of colors from blue to green to red, and the solution, the colors are distributed uniformly. So you can see the this isosurface or contour values are displayed uniformly. We can change this to logarithmic, we'll see that later. Now we can choose this option called reverse rainbow. If you do that, you will see that the colors have been reversed. So red represents the minimum value 0.876 and blue represents the maximum value 1.0. Remove this. Now the user can also display the contours in a grayscale, going from white to black and a lot of gray shades in between. So black represents the minimum value, white represents the maximum value, and various shades of gray in the middle. Let us change back to rainbow. Click on close. Now go back to file again and choose the view project files option. Now scroll down here, you will see a file called project1.out. Click on this. Now this is a very important file that is created when the problem is solved by PORFLOW. At the top of this file, you will see some information about the software which is used, PORFLOW. You scroll down, you will see what version of PORFLOW we are using, when the case was run, how long it took to run. You will see some information about the license, and then you will see each line of the input file is displayed here or written here, and sometimes you may see a comment about what action the solver took while processing that input. So all the inputs are listed here, and you can see sometimes there are some comments. We will analyze this later in a different video. Now if you come down further, you will see some information about the grid. Since this grid is orthogonal, the orthogonality index is 1.0. It's perfectly orthogonal. There is no non-uniformity. The grid is uniform. There is no skewness. And you can see some more information about the mesh. Scroll down further. You will see some details about the coordinates. And then you will see some geometric information such as the total volume of the elements, volume of the fluids and solid, and so on. Come down further, you will see more information about the variables which are going to be displayed during the solution process, and various options for diffusion and convection, and the linear solver where you're going to use the default ADI solver for this project, and the convection scheme will be the hybrid scheme. So all this information is written in the .out file. Finally, if you come down further, you will see the what is called the diagnostic and convergence output. This displays for each time step, or as frequently as the user requires, the step number, the time, and the value of the species, and some residuals and other things. This C is the value of the species C at one particular location in the grid. And if you go above, you will note the diagnostic values are displayed at element number 5. So this is displayed, and after the problem is solved, you can see there is a section called balance summary. This is extremely important. We will see in a later video how to understand this balance summary. We will see the next net flux disparity is 10 power minus 16. So the flux balance is almost at machine tolerance, 10 power minus 16. You can close. So that is how you solve a species diffusion problem in a saturated porous media using structured grid. Now click on file, and you can exit and click on yes.